Alright, thank you everybody for coming to ACM today. Today's presentation is going to be on functional programming. I don't remember. You're Jonathan Romwell. Jonathan Romwell is doing the presentation on functional programming, which, by the way, is actual type of programming that you do with programming languages specifically supported. It's not like a convention that you can apply in just any language. So, first off, we're going to start with a prayer. So would somebody like to volunteer for that? Yes, Gage?
Dear Heavenly Father, we thank you for this time that we can get together and learn about new concepts and special minds. We've also felt like we're inspired and be able to ask good questions and be able to grow together.
Amen. Amen. Okay. Great. So, we've got committee reports, and we'll do presentation. We always do this. Barry is currently walking about the hall on a phone call, so we'll come back to him. Doug's not here. We'll come back to him if he comes here. Online committee. Where it is that you want, your forehead, I don't care. It's your sticker. But we want to have a nice design, so that's the competition for. Artificial Intelligence Committee. Okay, so this is the deal. The, what?
No, it was...
The AI Committee chair, Michael Collette, he had to resign because he got an internship. So there is no more AI Committee. We got somebody who wanted to do to be the chair of the AI Committee, but there's already one that exists, and on top of that, there hasn't been a lot of interest lately. So we're going to focus our energies on a world without the committee, and if you are still interested in AI, there's a society for that. They meet every Tuesday at 5 p.m. over in room 214. So if you're into that kind of thing, then you can do that. All right, Co-Challenge Committee. Alan Morgan is not here today. He's at a family reunion, so I'm going to have to talk for him. There's a Steam gift card. Interesting fact. When we tried to have people come to CodeSpace, which is where we do code challenges, and we had the Steam gift card as an incentive, we didn't get nearly as many people as we did last time, and our guess is there wasn't food. We had $20 Steam gift cards, so that way you can be ready for the Steam gift card sale. Not Steam gift card sale. The Steam summer sale, which is supposed to start in July, by the way. And if you have money in your bank account and you're into games, expect for it to be gone by the time that happens, because it's Attack on Gaben. If you don't get the reference, you should check your email. I'm sure I sent it to all of you guys. There's a lot of memes with Gabe Newell and Steam sales involved. All praise to Gabe, I guess. So, Gabe Newell is the CEO of Valve, who is in charge of the Steam store. So that's why. It's the joke if you don't get it. All right, next. Going back to guest speaker officer. Your turn.
Oh, goodness. I have been out of town, so...
He's back. He's awesome.
Good. I gotta pull it up. I'm sorry.
It is confirmed next week, by the way.
Oh, it's functional programming, right?
Today.
Oh, that's right. It's you. I haven't seen you face to face. Sorry about that. Okay. Very well, just-
So next week we've got Clearwater coming to visit,
Right.
and they're an employer, and I'm pretty sure Jolly likes them. We could talk to him about them. He likes them. So they're a good company. So then, what comes after that week? Well, we got something very special planned. It's something that I kind of like thought of doing since the beginning of the semester, which should definitely attract people's attention. We're trying to give all of you an opportunity to have a simulated, hardcore programming job interview sort of a thing. We're going to have 3 companies that be fake companies, and we're going to have members of the faculty available, and they will do an interview based off of the company persona that we have developed. These 3 companies are a game development company, a defense contractor, and then of course an internet company, which are pretty big in Silicon Valley. And so these are the 3 companies that we have that we are developing personas for, and so we want them to give you a hard time. And the reason why is a real interview is typically not a cakewalk. They want to spend enough time to figure out whether or not you are a hire or you are not worth our time sort of a deal. And if you're like me, I totally bombed my first interview. It was a pretty bad experience, traumatizing. So we want to make sure that if you're going to bomb an interview, it will be with our faculty. And that way you can have a pretty good expectation of what a programming job type interview would be like. We're putting a lot of effort into this. This is next week. We're going to put posters up ahead of time, and you guys have notice. We're going to also put up a sort of a fake job post on one of the bulletin boards out there, so that way you can look at them and see what they're going to expect from you. And of course, those job posts aren't going to be the complete picture of what this company is looking for. They've got no hire criteria. They've got hiring criteria. They have, the person that is going to interview knows the company better than you will know it and what's going on in the background and things like that. So there's going to be questions that you aren't going to be prepared for, and you better be ready for that. It's just part of the experience. We're trying to make it as realistic as possible. We cannot allocate an hour to each one of you. So it's going to be a very compact type interview, and then you're going to get feedback from the faculty on how you did and what you could do better. So we want you to be prepared for that. Are you all interested in this? It's great practice. It's better than what they can do down over at the Academic Discovery Center, the Career Center. It's much better because they aren't going to be giving you technical interview questions there. All right? So that's it. I'm going to turn the time over to Jonathan Romrell, and he can give you the presentation on functional programming. All right. Yay! My screen up?
Yes.
Good, it's not changing.
Well, hello, my name is Jonathan Romrell. As a brief introduction, I'm going to be talking about functional and data-first programming in Clojure today. I have had a lot of experience in the workforce. I've had 7 internships up to this point, having started early in high school. So I have many years of working with different companies, different teams. I have a fair amount of experience about programming in the workplace. And so functional programming I picked up during my last internship at Clearwater Clojure for a project, and ended up spending a lot of my internship working in Clojure. And I've grown to fall in love with functional programming and with Clojure, and I think there's a lot of advantages to them that I'm going to describe to you here. So what is functional programming? Well, functional programming came about kind of as a result of lambda calculus. I'm not going to go into crazy depth with the math here, but the idea is that functions are a mathematical construct in lambda calculus. This means a couple of things. So functions are infinitely composable. In math, you can have a function that has another function within it, another function within that. This is somewhat familiar to us in other programming languages as well. The same principle tends to hold true. Functions can be partially defined or evaluated using a technique called currying. And that is here, if I have the distance formula that takes in x and y, I can represent that as a function of only x that returns a function that takes y that returns my result, or I can represent that as a function of only y that returns a function that takes x. And in pure lambda calculus functional programming, technically functions only ever have one argument, and they're chained together in this way. And this has the benefit of being able to partially define and partially evaluate functions, because here I can say, given that x equals 3, I can take the same function and return y equals 9 plus y squared. And so I've done a part of the evaluation already, despite not having all of the arguments yet. So there's some advantages to this that you get in functional programming that you don't often see elsewhere. The last thing that's really important is functions in lambda calculus and in functional programming always map the same inputs to the same outputs. When you're working with algebra, you never have y equals 3x plus 2. If you give a value of x, it will always return the same y. And this is true in functions and functional programming. This means that a true function doesn't have randomness inside of it. It doesn't work with, it doesn't have side effects where it'll go off and change your code in other places. And it doesn't work with mutable states. So you aren't taking an input from somewhere else. You aren't checking values that are somewhere else in your program. The function's entirely self-contained. Somehow this got changed to black text and got hard to do one.
You just lost video?
Yeah, it's just trying to catch up with them.
Okay. Give this a second chance. Okay, well, we'll see if it ends up working out or not, but I can talk over the slide like I would have normally do anyways. So here, this is an example of a function that exists in Java graphics. So here you have graphics.fillRect given arguments 0, 0, 500, 500 for positions. So this, as people who have worked with Java graphics at all know, is taking and is drawing a filled-in rectangle. And so the first two arguments are positions x1, y1, and the second two are x2, y2. So I have a few questions about this. The first question is, what color is the rectangle? Does anyone know? It's impossible to tell just from looking at this. The graphics object has color as a member variable inside of it that's kind of hidden away. And so what you do is you can use getters and setters to change that member variable. So before you call fillRect, you might set color to red or green or black. But looking at this code, you have no way to tell. You have no way to tell what the color was set to last unless you set it every single time. And you run into a problem if things are multi-threaded and you have a lot of threads competing. You might set the color to one thing, go, and before you even start filling in the rectangle, the color can change underneath you. So the next question, where's the rectangle being drawn? Does anyone know? Yeah, so it's being drawn on graphics, and graphics as a member variable has a component, a canvas essentially. It gets a little bit confusing because the canvas also has graphics as a member variable, so there's kind of this interwoven relationship there, but it's really hard to tell from this. You don't know which canvas it's being drawn on. This code would look the same if you're drawing on another canvas. The next question is a little bit more complicated. What happens when another thread displays the canvas while this function's running and a rectangle is being drawn? Bad things happen. So if anyone's familiar with screen tearing, this commonly occurs in games or other things. You'll have the rectangle being drawn line by line down the screen, and partway through that, you'll end up with it being thrown onto the screen, and you'll see a tear across the screen, or across the rectangle in this case. where it's not finished drawing yet, so things look wrong. And the last question is, if something breaks, if there's a bug, what could be to blame? I'm seeing shaking heads. So there's a couple of things that could be to blame. First thing is you could have passed in bad arguments. If you pass in something that's not a number, or you pass in something larger or smaller than you want, you're going to get a different result than you expect. Next thing that could be wrong, fill rect could have been written poorly. The programmer could have made a mistake developing the function. There could be a bug inside of it. The next thing, we talked about there being color and canvas elsewhere. Those things could be messed up. So there could be something wrong with graphics. There could be something wrong with the canvas you're drawing to. Or there could be another thread doing something that ends up interrupting and causing problems. So the answer is, what could be to blame? The rest of your program. You really have to go, and there's things you can do to kind of make it easier, but you're searching through your entire domain of the program to try to find the bug. Oh. Well, that'll make it easier going forward. So now a functional equivalent of the same function. So here you have fill rect. Let's answer these questions. What color is the rectangle? Red. It's obvious. Where is the rectangle being drawn? Canvas. You see it right there. What happens here, this one's a little more complicated again, when another thread displays the canvas on the screen while the rectangle is being drawn. And I'll just go ahead and answer this one. In functional programming, values are immutable. And so what that means is as you are doing transformations on canvas, as you're changing things, you are creating a new copy of canvas. You're never modifying the original. And so as a result, the other thread is working with the original, and they can throw the original up on the screen anytime they want without worrying about other functions having broken the reference they have. So you get what you expect. The rectangle isn't finished being drawn. Let's display the image without the rectangle. The last question, if something breaks, what could be to blame? Now, here in functional programming, you still have the same first two problems. You could be providing bad arguments, or the function could have been written poorly. But that's all. There's no immutability, there's no state. So you don't have to worry about other threads. Other threads don't affect this because this is working with its own copies of these values. You don't have to worry about other objects or constructs elsewhere in your code having an effect on this function. It's entirely self-contained. So going through the benefits of each of these, so asking about what color, we see here there's no mutable state to wonder about. The function is given all that it needs, whereas the rectangle being drawn. Functions don't belong to objects. They work the same no matter what context they are called from. What happens when another thread displays the canvas to the screen while the rectangle is being drawn? Functional programming is thread safe. No code change is necessary to use concurrency. And as long as you're following functional programming practices, this will always be true. There are cases in functional programming where you might not have pure functions. You might need to use randomness. You might need to use state. And most languages have safe ways to do that. But in general, no code change is necessary to be able to use threading, which is a huge advantage. And then lastly, if something breaks, what could be to blame? As I mentioned, functions are self-contained. This also means that they're very, very easy to test. When something goes wrong, you can kind of picture your software. You have a main function somewhere, and that chains off into a bunch of other functions, and you have this big tree of functions that are being called. And testing in a language like Java or C++, it's not really a tree. It's this big interconnected graph, and it's really hard to trace things through. In functional programming, it's always a tree, and you can always say, okay, I can identify this branch is wrong. Then you can go follow down, and it's always one direction. You don't have to ever go back or worry about functions you've already passed or already looked at. So the question then, which one would you rather use? And which behavior is default in the languages and the technologies you're using? I think which behavior is default is really important because when we are programming, we tend to use whatever's most readily available to us. It's possible to program functionally in a language like Java or in C++, You can follow these practices. There are immutable data structures if you go and look for the right libraries. But it's hard, so we don't do it. So here, in general, this is very rough. Up here we have object-oriented programming and to an extent procedural programming as well. Here's common languages we see, where some of these you look at Lisp and say, okay, I've heard Lisp connected with functional programming. And yes, Lisp is known for being able to do functional programming. But immutability is not default in Lisp. You have the ability, anyone who's taken algorithms and complexity with whether or not, see plenty of examples of times where there's still state, where things end up still being really complicated as a result of not following the functional programming practices. So the question here is really not can you program functionally, it's what's default. And so here, functional programming on the bottom, you have immutable values, stateless functions, easy concurrency, and you get languages like Clojure and Haskell, and there's a couple of others as well. There's not as many, but they're becoming more and more popular, and we're starting to see a lot more languages and derivatives of these languages appear. So Clojure is a modern Lisp. Give you guys a moment to read the comment. So anyone who's worked with Lisp is very familiar with parentheses, and we'll get there in just a moment. So in Clojure specifically, you have these primitive types, and these are all of the primitive types. One of the things that Clojure really aims to do is to have a massive amount of functions that operate on very few types and structures. And so I will get into the benefits of that a little later, but you have nil, you have your Booleans, true and false. Clojure is truthy by nature, which means everything is considered true besides false and nil. So it's very easy to test the existence of something just by saying, if the value, do this. You have numbers, so you have integer, and also has a big integer kind of behind the scenes if the number gets too big. Decimal, same thing with big decimal, so you can keep precision. And Clojure has a ratio class, or a ratio primitive. The ratio allows you to keep precision when you're doing division operations. Here, if you take 127 and divide it by 93, you'll end up with some decimal, and it ends up usually being a good approximation if you're using a double. But this allows you to get the exact value when you go and multiply it by 93 again, or do something where you can simplify it later. You get strings, characters, and keywords. Keywords are just strings that are only stored in memory points. So whenever I use the name keyword, all name keywords in my program are pointing to the same location in memory that never changes. So that you don't modify keywords, they just exist. You get collections. You have lists, vector maps, sets. You have sequences, which are lazily evaluated lists. And for the most part, this is really it. It's, again, you want lots of functions and few types and structures. You'll notice here that you can have mixed values within any of these structures. It's not like Java or C++ where you have a list of integers or a list of strings. You just simply have a list and you can stick whatever you want in there. So maps here is the one thing where there's maybe a bit of a question that comes up about the syntax. And technically, you don't even need the commas if you don't want. They're optional. But every other value is a key. Every other value is a value that's paired to the prior key. In Clojure, you have code as data. That means that lists are, or in Lisp at least, lists are assumed to be code and they will automatically be evaluated. So your code is simply a bunch of lists with functions as the first item and arguments as the rest. So here, this is a list where the first item in the list is the addition function, and then you have the arguments 1, 2, and 3. So if you write that in Clojure, it will evaluate to 6. To avoid evaluation, a list must be quoted with a single tick in front of it. So that way you can represent the same thing, put a tick in front of it, it won't evaluate, and you can pass it around and modify it later if you want. Question?
So in that second one,
Without the tick, it would automatically sum it. Is that like the default thing that lists do? Is they sum up whatever's in the list?
No, so here, when you don't have a tick, it assumes that it's a form, it assumes it's code, and the function must be in the first position. So here, this was a division operation, I would do a divide instead. Here, it's, these aren't equivalent, I could have a plus here as well. It doesn't evaluate because there's the tick. So I can have a list of functions that I'm passing around, or in this case, a list of integers or a list of other mixed types. And it just simply doesn't evaluate because it's coded.
If you take the tick off, it'll try to run 1 as the function,
Okay.
and so it'll break, yeah.
Okay.
So just to clarify.
Yeah, and so the tick's necessary whenever you're making a list literal that you're wanting to work with. So now you have simple functions. So here you have an increment function. It works as you'd expect. You have addition. Notice that addition can have an arbitrary number of arguments. So a lot of closure functions are this way. So I can add 4 on the end of this, and suddenly I'll get 10. I can add 2 things. I can add 1 thing, and it just returns itself. Then you can have predicates, which are also just simply functions. So here it's testing to see if that value is even. Then here, string concatenates it caches all the following values to strings and concatenates them. Conj will add a value into a collection, and Clojure is amazing about having type agnostic functions. So it doesn't matter what types are in the collection, what type you're adding, and it doesn't even matter what the collection is. You can conj into a vector, you can conj into a list, you can conj a key value pair into a map, you can conj into a set, and conj just adds it in whatever way is most performant for that structure. So for a vector, it being similar to like an array or an array list or something, it's fastest to add on to the end. With a list, it's fastest to add to the beginning because it's backed by essentially a linked list. You have a soak is a cleaner way of associating a value to a key in a map. You can do the same thing by wrapping this in a vector and having conj, but this is a little bit cleaner to work with when you're working with maps. Interestingly enough, with vectors and lists, you can treat them as if they are maps with numbers as keys, their indexes as keys. So I can soak into a vector, and I can associate the value at 0 with 4, and it would replace the value at 0 with 4. And then count. There's a lot more functions. I'm just going over a couple of simple things so you can understand some of the code that I'll be showing later. You can nest forms together kind of as you'd expect. Things evaluate from the inside out. So here I can take the difference between 2 numbers, I could add them up together, and then I can use the greater than function. And this isn't simply is x greater than y, it's actually saying is all of the following arguments strictly decreasing, which has a lot of use. So here this is true because these are strictly decreasing, but if I throw another 8 at the end of that, it would return false. Similarly, string, it'll evaluate all of this math first before it concatenates things together. So you can define functions. There are several different ways to do this. This is kind of the typical way up here. You have def_n is actually a function itself. Everything in Clojure is functions. So def_n is a function that takes the symbol, the name of your function as the first argument. It takes a vector of symbols as the next argument, and these end up being parameters inside of the function. And then it takes a single value for the code you're going to do there. And so it's possible if you're needing to do multiple things to wrap them in some other construct, but you need a single value there at the end of your function. You can have a verbose version of the anonymous function here. This specifically says that I have A and B as parameters. Or you can have a really, really concise version of the anonymous function where the number of parameters is unknown, it's undefined. So here this is saying the first argument, whatever it is, and the second argument, whatever it is, let's add them. And so you can call this function, pass in 5 arguments or whatever, and it'll work with just the first 2. If you try to reference the second argument and only 1 argument is provided, you'll get errors then. but very, very flexible and allows you to be very concise while expressing the creations of these functions later on. So functional programming process. The idea behind programming and functional programming is simply data in, data out. You define or describe your starting data. You figure out what you want your code to do, what you want returned, where you want to go, and then you use functions to get from A to B. So functional programming, when it comes down to it, is all about data transformation. And really, I think most programming we do is all about data transformation. There's very little that you can't represent as data, because when it comes down to it, everything ends up in memory and it must be data in one way or another. So functional programming, and specifically Clojure, is excellent at this and stands out above other languages, in my opinion, when it comes to data transformation, which makes programming much easier. So we get into transducers now. These are transformation functions, and they can be extremely powerful. So here you map a function onto some sort of collection. So in this case, I'm mapping the increment function onto a vector with 1, 2, and 3, and it returns 2, 3, and 4. Again, type agnostic, stick whatever collections you want in there, and it will do it just fine. You have reduce. Reduce works by applying this function to the first two arguments, so it will concatenate A and B, and then it will take the result of that and apply the function to the result in the next one, and then the result of that in the next one, all the way down the list. So it's a very easy way to chain and reduce things down. So if you had a reduce with a plus here, it would go and add all of these up just in one line very simply. Very, very powerful. In other languages, you need to worry about all the minutiae along the way. You're worrying about, I have this counter here that I'm incrementing, I'm decrementing, I'm changing, I have a state here, I'm having to walk over a list. And it ends up being several lines of code to do what really is one thought, one process. And Clojure is excellent about having a lot of very powerful functions that represent one transformation, one thought, one process. And so once you learn the syntax and learn the language, programming becomes much more like thinking. You're thinking through a problem, thinking, I need to transform this in this way. There's a function for that. I'm needing to transform it again in another way. There's another function for that. Yes?
So in functional programming, the concept of object is primitive always, right? Is that right?
Yes, and I'll get into that in a little bit.
But I have seen this concept of map and reduce used in like lists of objects that might be more complex, but we're calling, for example, a function that exists inside of this object, and then we get all the outputs of these objects, and then you're able to reduce that output into something like a report.
Yeah, that question I think might be a little bit easier to address later on in the presentation. I'll be getting there and showing you more complicated examples. So you have a filter function, which takes a predicate, something that will return true or false. And it goes and applies that predicate to every value in whatever collection it is and returns only a collection of the values that the predicate returns true for. So in Lisp, again, to make the comparison, because Clojure is very Lisp-like, the transducer functions are not collection agnostic. You have map_car for list, map_hash for maps, etc. In Clojure, you just simply have map, and you can use it universally, and it's very powerful and makes the language a lot easier to learn. I tried working with Lisp a little bit, and it was just really frustrating for me to try to learn because there's just so many different functions out there, and it's really hard to tell which one you need in which scenario. So here's something that I've had to do recently, sentiment analysis. This is showing the functional programming process a little bit more. So I define my starting data. Sentiment analysis is taking a collection of sentiment for word values. So here, happy is a positive value, so it's a positive word. Sad has a negative value, so it's a negative word. Okay is a little bit more neutral than happy is, but it's still slightly positive. And then you take in one or more messages, and your goal is to determine if these messages overall have a positive, negative, or neutral sentiment. This is used a lot in the real world for looking through like social media and trying to determine how people are reacting to a product or a marketing scheme or something. You're wanting to very quickly and programmatically be able to go through a lot of data to see are people happy about this or not. So my desired data is I'm wanting to transform the collection of messages into a collection of sentiment scores. So I have my starting data, I have my desired data. So the next question is, how do I get from A to B? And very simple. In other languages, this is a lot more verbose. I've tried to do this in Java, and it's definitely possible. But once you learn this, it feels a lot easier to work with. So here I have a function called score text. This takes in a sentiment map, and that's the sentiment map we saw in the other in the previous slide. And you take in a single text post, a string. I say let this words be splitting the text by a space. This just means regex, having the pound sign before it. So I split the text by space, and now I have a collection of words. Now, word scores, I am mapping this onto words, where this is checking for the word in sentiment map, and if it exists, I am just returning the score that it's mapped to. If it doesn't exist, then I return 0 and assume that it's neutral. So here I'm mapping this function onto my collection of words, and now I have a collection of word scores. And now I simply reduce and I add all of those together. And if I have a lot of very positive word scores, I end up with a very positive sentiment. If I end up with a mix of them, I might end up with neutral. And if I end up with very poor word scores, it ends up summing to a negative number. Now here I score all messages. This takes in my collection of messages you saw earlier. So here I am mapping this function with the sentiment map onto each message in messages. So the syntax probably looks unfamiliar, but I hope that this helps kind of demonstrate the point where functional programming really simplifies the programming process. Nowhere in here am I having to manually think about a loop and all of these temporary variables I have along the way. I'm not having to worry about building up or breaking down collections or anything like that. I'm just worried about process every step of the way. How am I transforming this next? So I'm going to talk a little bit about object-oriented programming, kind of the top-down process in contrast to this. So the top-down design process, you first ask the question, what are the components that exist in the system and what are their relationships? And then the next question is, have I sufficiently decomposed the system? And whenever the answer to this is no, you have to go back up to this first step and break apart your objects some more. So let's design a tabletop game engine. So here are our components. We have an interface representing some abstract sort of game, and we have a class that interfaces with that interface. It's an actual instantiation of it. So we have all of the components of our system here. This represents any game, but it's not sufficiently decomposed. We can't go and just program a single game class and know what we're doing. So we have to break it down further. So we can find the definition of a game. A game is a system in which players engage in an artificial conflict defined by rules that results in a quantifiable outcome. So here, many of you have probably done object-oriented programming. We're looking for nouns. What are the nouns in here? What objects might we have? Okay, so we have player, we have system,
Combat. Oh, I don't know.
Rules. So here we have a game now. Has a collection of rules and a collection of players. We have an interface for a rule, an interface for a player where we describe what those are. We have concrete implementations of each, and we have a concrete implementation of our game. Is this enough for us to know what we're doing programming a game engine? No, not even close. So now we have to handle different types of games. So we have in here a board game, we have dice, we have a deck and cards, and this is going to get more and more difficult to read. but it gets more and more complicated. Now we have board and card games that aren't as simple as was represented in the previous one. Here we have a board game with cards. We have a board made out of cards. And we have these unusual relationships between things that weren't captured in the previous slides. So now we have to look at multiple inheritance. We have to find ways to be able to allow all of these complicated relationships to occur. So it continues to grow. At this point, maybe it's time to reevaluate what we're doing. Because this can continue to grow and grow and grow as we're trying to approach this problem. And it's a little easier if we know we're tackling an individual game because we can prune and toss some of this out. But it still is getting ridiculous pretty quick. So I'm borrowing here from a presentation that a colleague of mine gave at my last internship. And he wanted to show an object-oriented approach to a specific game and a functional programming approach to that same game. So he used the game Cartagena, and probably none of you are familiar with it, but it has a couple of simple rules. So you see here there's a board. Each player has several players, pirates, that are colored. They start with 6 random cards, and a player gets 3 actions each turn. An action can be spent to play a card and move the pirate forward to the next symbol matching the card. You can move a pirate backwards to earn more cards, or you can pass and end your turn. The first player to get all of their pirates to the ship at the end wins. So here you have what appears to be a very, very simple game. You can teach this to a toddler. It's very, very simple rules. But it gets pretty complicated. So here we have all of the different objects, and in some of these you can kind of cheat a little bit and not fully represent the object. You might represent it in some smaller way. But you have to keep track of the turns. You have to represent the cards. You represent the board. You have to represent the different actions that you're allowed to do. And it gets big. So this is my coworker's approach, and he maybe exaggerated a little with this. But he ended up with 22 classes, 11 interfaces, and 1 enumeration. With no implementation, only representing classes and their relationships, this ended up being 271 lines of code in Java before doing a single thing. So let's try this in functional programming or data-first design. So we want to say, what does the starting data look like? What should my output data look like? What functions do I need to get from A to B? So the starting data is really simple. You have your players, and each player picks a color. So here, whoops. So here, I might be playing this game, and I picked green. Mark picked yellow. Bob picked blue. Very simple data to start. Well, in order to initialize and start the game, we need to transform that into this. So this looks a little bit ugly, but when it comes down to it, it's really simple. You have a turn order. Here it's a map of if it's yellow's turn, blue's turn's next. If it's blue's turn, it's green's next, green, then yellow. You have a collection of players. A player is represented by the color they picked, because if you represent it by their name or something, people might have duplicate names, and that doesn't work. So a player has their color which they're identified with, their name, has the number of each type of card they have, and the number of actions they have left this turn. And so that's this entire middle part. It's just 3 players with a couple of simple attributes each. Then lastly, you have a board. A board, as you saw earlier, is a collection of these tiles with symbols on them. So you have a symbol for start, a symbol for sword, for hat, and so on. And each of those has the number of pieces of each color on it. So everyone starts with all of their characters in the starting position. But when I move yellow forward to the next hat, I'll end up with a 1 here and a 5 there because I moved a piece along. So I somehow need to get from the starting data to this. With this all defined the way it is, this ends up being a very easy process. So what functions do we need? We need generators. Generators in these cases are technically not functions because there's sometimes randomness involved. They're like when you're drawing cards, there's randomness there. They're creating something out of nothing, and that something's not always the same every time. So we need to be able to generate cards, we need to generate the board sequence, the turn sequence, so on. And we need an initializer that puts everything together. So here are our generators in Clojure. We represent all the different card types so that we can work with it later. We have a draw function, we have a function that generates a board sequence, and we have a function that creates a turn sequence. Now for player initialization, we need a function that puts cards into a player's hand. So here we have a multi-arity function. So here we have a hand and a single card, or we have a hand and multiple cards that we're putting in. And we have functions that handle those. We have a function that builds an empty hand. We have a function that initializes the hand by drawing 6 cards into an empty hand. And we have init players that applies this initial hand into every player and creates the player constructs we saw earlier. We have board initialization, where we add the initial pieces onto board, where we make the board and put everything in order and set up board that calls these 2 functions. And we have game initialization, where we put it all together into the one map we saw earlier, and we're done. We aren't playing the game yet, but this is far beyond what the UML diagram for Java showed earlier. We actually have done stuff and actually built up the entire game and we're ready to play now. It ends up being 32 lines of code total, and some of these lines are a little dense. It's not my code. But this is dramatically simpler than the object-oriented approach. It's a lot easier to see where you're going. It's a lot easier to get from A to B. I hope that you guys can kind of imply into this, if we were to actually go play the game, the functions from there are all small and simple as well. It's just transformations, and Clojure is great at that. So I can transform from one game state to another. If I move this token onto this tile, that's a very simple transformation. And it's very simple to see at the game's ended. So the entire game ends up being very simple and easy to tackle. Yes.
Can you go back to the previous functions that you showed? So, generators.
So I'm not going to dive deep into these. I'm happy to talk about these afterwards with anyone, but I have a couple of other points I wanted to hit. But the idea is you have the generators are just creating things out of nothing. Here data in, data out. This approach makes implementation obvious and often even trivial. We can take large and complicated problems, and when we represent this as, here's our starting data, here's where we want to go, it's very easy to say, well, I changed this value into these values, I do this to this, and it's very simple steps. It makes the process very easy to break down. Functions are infinitely composable. I can have functions within functions as much as I want. This contrasted to object-oriented programming, objects are not. I can't have objects within objects within objects. You can to an extent, but as you get into these complicated inheritance relationships, you end up having to create more and more interfaces. If I want to have a list of mixed types of objects, I have to create an interface that describes all of that object, all of those objects. And it ends up that the number of objects and the number of interfaces you have kind of grows exponentially as the project gets larger and larger and as you have to do more things. Small functions can be composed with other small functions to increase capability without increasing function size. Each of those functions, while a little bit dense, was only a couple of lines. Very easy to visualize once you are familiar with the language. Easy to visualize and know what that function does without having to understand the rest of your program or without having to look at 50 lines of code. And I mentioned objects not being very composable. So a few more observations. There are easy and hard ways of programming. So here are a couple of takeaways from this example. Abstraction is hard. When we're working with objects, when we're working with interfaces, when we're working with some of these things, it's hard. There's some benefit to it in some cases. Constantly work through those abstractions and smugs things up and makes it hard to connect things together. Data in comparison is easy. You have a few different types of data, a few different collections, and lots of functions and tools to work with. Getters and setters are hard. You spend a lot of your time in an object working on how do I figure out how to get or change data in this object. Whereas in Clojure or functional programming, you end up with these transducers that will make these massive changes for you in a single step while still being very customizable, very easy to understand. So I'd argue that these are easier than having to write getters and setters for every member variable that you create. Procedure is hard, transformation is easy. Procedure is poorly worded, but what I'm trying to represent here is if I am wanting to reduce something or map something or filter something or one of the many other transducers that Clojure has, Clojure views that as a transformation. It's a single step. It's a process in other languages. You have to write out that for loop. You have to figure out how you're walking over the collection. You have to figure out where you're keeping state, how you're doing things every step of the way. And you have to think through all of these things that aren't really related to the problem you're trying to solve. You're worried about syntax, not the problem. Uniformity is hard. Flexibility is easy. And by this, I mean in terms of the data. In Java and C++, you have collections that can only have one type. And so you have to create interfaces to represent things that are slightly different and get them in the same list. And that's hard to work with because you often want to put different things in the same collection. In the real world, you often have things that are slightly different. This is especially true in my last internship at Clearwater. We were working with financial information. They're never consistent. Every loan's a little different. Every different possible investment out there is slightly different. There's general rules things are supposed to follow, but they get broken. And so we have to handle those somehow still. So this gets into this next one. Inheritance is hard. Commonality is easy. It's easy to represent things, and I'll get into this, as there being similarity in the data and working with that similarity, not saying these have to be the same thing. So here, I have a person, a dog, and a tree, and I'm wanting to write a set name and change name function. Person and a dog has a name. A tree doesn't. A bear doesn't. A monster might or might not. Whatever you're working with, it has a name or it doesn't. But wouldn't it be great if we could toss all of these things into a list and apply a single function to it and have it do what we want? And really the question there is, what do we want? So set name sets name regardless of what the old name was. So if I call set name on all of these objects and set the name to foo, a tree will end up with the name foo. And sometimes that's what you want. Sometimes you get people who name trees or cars or whatever else. So sometimes you will toss something unexpected into a collection and want to do something unusual with it because unusual things exist in the real world. Here, this is maybe a little bit more what you'd expect. It only replaces name if it exists. And both of these, using some of Clojure's cool functions, end up being single lines of code. But this gives you the flexibility to set the name as necessary. You can have a list of all sorts of things, and it'll override the name where you want it to and not where you don't. So here we're working with commonality. What is the same between one piece of data and another? We aren't having to work with these differences where we have to say a person and a dog are both living things. Well, so is a tree. So maybe a person and a dog are both animals or creatures or something. But a bear is a creature, and bears aren't often named. And so you run into this complicated problem when you're trying to fully define what all of these objects are and what they aren't, rather than just saying it's all data. What's common between them? So last couple slides. The benefits of functional programming, and some of these apply specifically to Clojure. You get faster, cheaper development. Those small functions where you're thinking in terms of transformation and processes are very fast and easy to write. From my experience, you end up spending more time per line of code because in Java or C++, you know how to iterate over lists, and so you're sitting here typing without thinking. Let's get rid of that. We shouldn't be typing just syntax just out of habit. any problem we're tackling, any work we're doing should be towards solving that problem and should involve thinking. So each line involves a little bit more thought, but you end up with far more concise, more maintainable code, and it's a lot easier to actually solve the problem. You solve the problem more quickly. You have simpler systems, which means cheaper maintenance down the road. You get a lot more flexibility out of functional programming and out of languages like Clojure that allow these mixed types. You get an emphasis on the process, which makes it much easier to visualize what's going on. When you're working in object-oriented programming languages, you are spending so much time thinking about inheritance, thinking about what belongs in an object and what doesn't. You're thinking about a lot of designing compositional things rather than how do I get from A to B, which is often a very simple problem. You end up closer to the data. When it comes down to it, the problem is I have this data in memory and I want to stick this data in memory, or I want to print this data out to the user or something. We just are trying to transform data when we're programming. But with object-oriented programming and some other programming paradigms, you end up having to work through these abstractions, having to work with objects and getters and setters and figuring out things rather than just transforming data. You have many functions with few types or structures, which allows the functions to support all the types and structures in the language very easily. It's very easy to write general purpose functions that can be used anywhere. And so you have a lot of powerful functions as a result. Other benefits include, and many of these are Clojure specific or list specific. You get code as data, you get the ability to do partial evaluation, function composition, out-of-the-box functions and transducers that come with the language that are very powerful. I have to actually implement a map or reduce in Java. In Clojure, it's actually built on the JVM. It's written in Java, the Clojure interpreter is, and you have the ability to interact with Java. So if you ever run into any problems where Clojure can't tackle it, or it's awkward in Clojure, you know that great Java library you love using, you can do that. You can use whatever Java tools are convenient, and it allows you to do it in a very concise way. You aren't writing Java code, it still looks like Clojure code, but you're able to call functions from within objects, you're able to pass whatever parameters you want. What about the downsides? In some ways, this was the hardest slide in the presentation for me. I may be a little bit biased, I love functional programming, but I like presenting a neutral, balanced viewpoint on things. So I'm going and researching online what are the downsides of functional programming. And when it comes down to it, very few exist. The biggest downside that a couple downsides people mention, performance. In functional programming, you're constantly copying data to maintain immutability. You have to worry about garbage collection to get rid of all those copies. This is offset by easy safe threading, often more than makes up for that. Being able to instantly parallelize your code and run it on a multi-core machine, often more than makes up for that. Also, the development and maintenance costs are almost always more expensive to companies than runtime costs. They spend much more paying their developers than it costs for them to run the server for a year. It's difficult to predict time and space costs of lazy evaluation. This only applies to a very specific subset of things you do in functional programming, and I had to hunt for this point a little bit. The last one, and a very common complaint, is the ramp up. It is hard. It's different. And I don't think this should be, he's learning it, and it requires a different mindset, a new way of thinking, learning a new language. And those things are hard. I don't think it should be an excuse for us not to adopt new practices and not to find ways to improve ourselves as developers. But it does require quite a bit of ramp up. It's a new thing. On this point, it is possible to apply these principles in other languages. I mentioned that briefly at the beginning. But even if you aren't learning Clojure, or even if you aren't working in Lisp, even if your company uses a different language that is not functional at all, you can still avoid writing that Java graphics function at the beginning and write the functional version of it instead. You can still use immutable data structures where possible. You can avoid unnecessarily having state everywhere. There's ways to apply these principles. Lastly, what have we learned from this presentation? briefly to cover the points. Define starting data, define the desired output, then the steps in between become simpler, often obvious. Immutable data leads to simpler programs. Compose functions, not objects, wherever possible. Less development effort and better maintainability often beat theoretical performance. It's a pre-optimization problem. Functional programming scales well. The free threading is huge in today's world. You can throw it on a 16-core machine or on a server farm with 20 16-core machines, and it will run fine out of the box. Enclosure might be worth checking out. I love the language. I've only spent a few months on it, but I've become a better developer as a result of having learned it. So that's my presentation. Here's a few resources that I used for creating the presentation talks that might be worth checking out. Thank you guys very much.
So we have CodeSpace tomorrow, and we still have Steam gift cards that we need to give away. But this time we are not going to be spending the rest of our budget on Steam gift cards. We're going to be spending it on food. So that would mean that in order to stretch it, we might have pizza, might have soda. We haven't figured that part out yet, but there will be food. So if that doesn't make you want to come to CodeSpace, then I don't know what will. But we're doing fun things there. We need people to actually make it fun. So if you don't come, then it sucks for us, because then we don't have you with us. So be there, or else I'll be more irritated next week. So I look forward to it. All right? And yes, we are planning to have, there is rumor that we will have some sort of LAN party thing going on eventually after hours, but that is not during the code challenge component. And yes, there will be a code challenge. I don't know what it is yet, since Alan's not going to be here. But we will also be giving away Steam gift cards because we bought them already. We can't take them back. They're gift cards. So, yes?
We're going to give out a Steam gift card for the logo.
Sure, if we have any left over. If somebody's able to do it, then great. See you next week or tomorrow. All right, I love you all. Bye.
I'm happy to stick around.